This is my dad. He is very much into billiards. And a few weeks ago, something was wrong with the horizontal leveling of his billiard table. He found out because, well, he actually missed a shot. So the question that popped up in my mind was, to which specification should a billiard table be leveled? Okay, before you think this video is about billiards, it's not. It's actually about me making a spirit level. And of course, I want this spirit level to be accurate enough so it can be used to check the level of a billiard table. Now, this video consists of two parts. If you are just curious about the actual manufacture of the spirit level, it's best to fast forward to approximately 5 minutes into this video. Now, if you're also interested in the details of the design process, please bear with me for the next 4 minutes. So, what kind of accuracy do we need to level a billiard table? Well, it's not a trivial question, and it very much depends on the maximum deviation of the balls that one would find acceptable. And every shot is different in angle, in power, in direction. Also, different types of billiard cloth have different friction coefficients, and all these parameters influence how much the leveling of the table influences the maximum deviation of the ball. Let's just consider an example. Let's just say you play a ball over the long side of the table and it rolls for about 4 seconds. Now, I did some calculations and experiments and I basically arrive at the following conclusion. In the described configuration and with the table under an angle of 1 degree, the deviation will be in the order of several hundreds of millimeters, so actually quite huge. With 0.1 degree, it will be in the order of a few tens of millimeters, and for 100th of a degree, the deviation will be in the order of several millimeters. Now, some of you may know from experience that the difference between a hit and a near miss is only a few millimeters, or even a few nanometers if you want. But if we accept the millimeter range, the billiard needs to be leveled with an accuracy of around 100th of a degree. A spirit level is basically just a bubble in a curved surface, and the maximum sensitivity is dependent on the curvature holding the bubble. Now, in theory, the larger the radius of the curvature, the more sensitive the movement of the bubble will be as a function of the tilt angle. And because of the required accuracy range, I wanted the sensitivity to be approximately 1 millimeter for each 100th of a degree of tilt. And this because 1 millimeter would be easily visible to the naked eye. Now, in addition, I wanted to have a measurement range of approximately 1 degree in total, so this means that the spirit level needs to be approximately 100 millimeters in diameter. As for the curvature of the surface, if 100 millimeter corresponds to just 1 degree, we can calculate the required radius in the surface, and this radius turns out to be approximately 5.7 meters, which is actually pretty big. And it also means that the curve in the surface of the spirit level is very shallow. As for the construction material, glass was the obvious choice for me personally because I have a lot of experience working on it. It's also transparent, it's very stiff, and therefore you can make very accurate shapes in it. And I decided to make the bubble level from 2 glass discs with the same diameter. In the detailed design, I focused on how to make the spirit level with the tools and materials that I had directly available in my workshop. And I had some borosilicate glass of around 50 millimeters thick left over from a previous project, so I decided to use this material. However, my biggest glass drill has an inner diameter of only 97 millimeters, so in my final design I chose the diameter somewhat smaller and chose the radius of curvature slightly smaller as well. In addition, I brought down the total measurement range to approximately 0.8 degree in total. Now, if you look at the CAD drawings, the surface with the curvature actually appears to be flat, and that's because the radius of curvature is over 5 meters. In the bottom part, I added a cavity for the bubble to move around, and this has a height of around 4 millimeters. I also designed a hole in the bottom to fill up the inner space with liquid and to insert a bubble. Now, in addition, I wanted it to be calibrated by design. So I know this sounds rather peculiar, but what I mean is that I wanted the accuracy of the two parts at a level where you could just, put them together without the further need of calibration. So to achieve this, you need to put very strict tolerances on, for example, the parallelicity of the edge of the lower part with respect to the bottom surface, and also on the flatness of the bottom cup and the centricity and the quality of the spherical surface. So that's what I did. I started out drilling 2 discs from a borosilicate plate, and this material by itself is pretty flat, but it's not flat enough for this purpose. So I grinded both sides of the 2 discs flat against each other by using a small amount of 1200 mesh silicon carbide suspension and very short strokes. Now the flatness and the roughness levels after grinding were in the order of only a few microns. Next I milled a pocket in the bottom disc with a diamond tool and drilled a hole through the center. Now because the result of the milling was kind of ugly, I cleaned it up a bit using additional grinding with some silicon carbide and a small glass disc. Now because I wanted the part to meet this previously described calibration by design, I needed to get the height of the edge as uniform as possible all around, and this could be achieved by fine grinding it against a very flat glass plate and by selectively applying more pressure on a specific side. And in this way I got the thickness variations on this edge in the order of 5 microns or less. Next is making the top part. Now the radius in this part is over 5 meters, and this requires a curvature of only 0.2 millimeters deep. So instead of milling a radius first, I just grinded a radius in the top disc using a third glass disc and some silicon carbide. So the way this works is that you concentrate your grinding action on the edges of one disc using the center area of a second glass disc. Now, due to the uneven material removal on both discs, one disc will automatically become concave and the other one will become convex. And then when you gradually go to smaller grains and to smaller strokes again, it's possible to end up with 2 spherical surfaces. By the way, if you want to know more about how to make a spherical surface in glass, I recently did a video on this subject, which will give you some background on grinding and polishing. So if you're interested, please check it out. There's a link in the description. The end result of the grinding is a very slightly concave surface in the top disc. And with this pherometer I checked the radius and it turned out to be 5.44 meters, which was good enough for me at this point. Later on I used this value to calculate the exact scale of the spirit level. I use optical pitch polishing to smooth the spherical surface, and after about half an hour the surface is nicely polished. And now it was time to make the edge on this glass, which can be used to connect the 2 pieces together. Now by carefully grinding the edge for a few minutes against a flat glass plate, I got a fine ground edge on the glass. Next is polishing. I polished the top surface since it was ground flat and optically not completely transparent. I also polished the 2 surfaces of contact between the 2 discs, and I did this because I had kind of a wild idea of how to connect them, which will be discussed in a minute. Now for polishing I used a home-built angular machine, and I will not discuss this machine here, but instead we'll get back to it in a future video. It's actually a heavily simplified version of the large angular machines that you find in the manufacture of flat optics, for example. And I'll post a link in the description to a YouTube video on such a machine. So basically the machine consists of a flat ring of pitch, and the object to be polished is held in such a way that it's freely spinning over the pitch ring, and it does not stay in the same position, but it's moved periodically over the extent of the ring from the inside to the outside and back. Now here you see that I added some weights on top of the glass disc to speed up the polishing process a bit. And here you see the result of the polishing of the edge next to the spherical surface. Now if you look really carefully, you can see the outer edge of 5 millimeters that reflects the light in a slightly different angle. Now in the same way I polished the surface of the rim on the bottom disc. So these surfaces were now very flat after polishing, let's say a quarter lambda. And while I was working on this, I figured out that it may be possible to connect the 2 pieces without glue by using a technique called optical contact bonding. So the idea of optical contact bonding is that you bond 2 surfaces together purely by molecular forces, the so-called van der Waals forces. And this is basically the same force that holds the molecules or atoms of a solid together. Now, why would I want to try this? Well, using this method could actually avoid uncertainties in the thickness of a glue layer that connects the two parts. So a variation in this thickness could actually screw up my so dearly desired internal calibration thing. But in order for this method to work, the surfaces have to be very clean and flat over the complete extent. So I tried it and it worked quite easily. Actually, in my very first attempt, the two parts connected so quickly and firmly that I did not even have the chance to get them aligned properly. Now, I tried to get the details of the process into view, but that was not very successful. So instead, I'll just post a few links to very nice videos showing you the bonding process in detail. Now, even though the contact bonding was successful, it turned out that the bond was actually not strong enough to withstand expansion of liquids between the two discs under temperature gradients. So if you put it in your pocket, it heats up and then it starts leaking. So eventually I just glued the two together using a very thin layer of UV curable epoxy. Next step was filling the cavity between the two discs. I used very cheap ethyl alcohol because of the lower viscosity and the lower surface tension compared to water. Now, the high surface tension of water actually inhibits the free flow of air bubbles, especially if the bubbles are small. Now, after filling and leaving an air bubble in the void, I sealed the backside with a small disc and some more UV epoxy. So here it is, the 1/100th of a degree accuracy bubble level. Next, I took it home and checked how horizontal things were in my house. And most things actually went off scale, although I was quite impressed with the level of our kitchen workspace. I added a quick scale on the back of the bottom part to get a better idea of the magnitude of the deviations. I just want to show you one more thing. Nowadays, everybody's carrying around bubble levels in the shape of a smartphone and an app. And some of them appear to have an accuracy of 0.1 degrees. Now, to see if this makes any sense, I leveled my spirit level to about 100th of a degree using sheets of paper. And I placed my smartphone on the top surface, which in this case is actually also very horizontal. Now, the smartphone displays a deviation of 1.8 degrees. But, is it the phone or is it the spirit level? So I rotated the phone on the surface, and what you see is that the error rotates exactly with the phone. It even shows the identical value in all directions. So this proves that it is the phone that is actually inaccurate by 1.8 degrees. And of course you can calibrate it, but it would require a surface better than, let's say, 0.1 degree horizontal. In the meantime, the balls on my dad's billiard table are rolling in razor straight lines, leaving no room for any errors. And that's it for this video. I hope you enjoyed it. Dag!